All right, welcome everyone to Portage County Safety Council. If you have not seen the first 4 videos of this, I encourage you to go back and check out sections 1 through 4. Today is 5 of 5 of our machine safety workshop. And let me tell you, I've been telling all the consultants across the state of Ohio about this presentation and the information that's here. So much good information, and I'm glad that we recorded it so that we can go back and rewatch some of these areas and take some more notes and implement it as consultants, and for businesses, start implementing these ideas and processes in your place of business to help keep everybody safe. So I won't take the floor anymore, but Mark, I just wanted to say thank you at this point for a great presentation thus far. All 4 sections were amazing. Looking forward to part 5 of 5. So it's all yours.
Well, I'm honored to be here, and I appreciate you guys and the interest in this as well. So as you said, this is the final chapter here, and the previous ones were recorded. There's some handouts and whatnot here too, and I mentioned this before about this form that was sent out earlier too to help take notes out and sort of categorize your thoughts, as you listen to this in these columns of dissatisfaction, the vision, and steps to get there, and then even resistance to change. So that change equation that we talked about as well. And also all of this is written up in this document as well. I think we provided that earlier. Today we're going to talk about, items that built on the previous sessions. Leading up to this, we talked about why is all of this happening, the societal demands, and what are the challenges, and what are companies seeing, and manufacturers, was what I'm really referring to. How have they responded to society's demands, and how has the law and the standards kept up to date with that as new technologies and techniques come roaring at this to solve this solution that society and in industry is requiring to implement. So then we talked the last 2 times on specifics on how to reduce risk, or the remediation methods, particularly with technology, the minor surfacing exception, and leading up to this last part of it, that with the assumption that we have all of this cool stuff installed, and we're depending on an electrical or pneumatic or hydraulic circuit to prevent that machine from actuating in a hazardous manner. How do we maintain that? How do we ensure that, 1, it was first installed properly, and then 2, how do we test it after installation? And then we're going to talk a bit about leveraging Industry 4.0 and give you, truly like a vision of a lot of companies are implementing this already, but the benefits of all of that stuff have been well renowned, and would continue to drive demand for sort of an interconnected solution. So we'll get into that. We'll spend a majority of our time on that today as well. But the first 4 sessions, it took us to get through the first 3 steps of the machine safety life cycle. We're going to finish up the last 2 in just 1 session here, but this will give you some context to where we are, with the process flow. So let's first start about installation. In particular, the safety engineered control solutions that we were talking about in the last session, the last 2 sessions in detail, require that they are installed properly. And we'll try to do some checking on this stuff after they've been installed, but there's some things that even the validation and testing won't cover. So there are contractors out there that are better than others at handling or installing these sophisticated machine safety solutions and the technology, be it hydraulic, pneumatic, electrical, electronics. So it's just something to keep in mind. The standards that guide all of that here are from NFPA and some IEC standards that look at how these items should be wired, how things should be routed and installed. And so some conventions that are good best practices for not only just electrical safety, but the installation of these electronic, electrical, pneumatic, and hydraulic solutions. So we're going to concentrate here primarily on the minor surfacing exception solutions that we talked about last week, the engineered controls aspect of it. Just a reminder, the default still is lockout, tagout, and fixed guarding. But when we are requiring access to a machine with energy on, all of those neat solutions that we came up with that are within the minor surfacing exception are listed here. We went through each of those as well. And, you know, you saw in the previous sessions as well, how much work and what goes behind putting solutions like this in. So, you know, if you ever hear somebody who may not be as familiar with the details, if you hear somebody say, hey, let's just put a light curtain on there, or hey, why don't we just put a safety mat there, or let's put a safety valve on there, you know, what goes into it. So that's why we touched on this aspect of performance level and the attributes of those circuits in here, the wiring structure, the reliability of it, the ability for it to diagnose itself. And when it comes into installation part of it, measures against common cause failure are really crucial. The performance levels in the chart that we showed you at least the calculations, and this, you know, about these first three attributes are all that really show up in the performance level calculations. The measures against common cause failure, which are really about how this thing is installed, where it's installed, what the environment is around it, is a pass-fail aspect of it. Essentially, if we can't guard against common cause failures or pass this test. So here's the test. It's a go, no go, a pass-fail aspect of it. If we can't pass this, all of what we just talked about, the performance level, the circuits, all of those solutions are not viable anymore. We cannot use those. We have to use something else. Design it out, inherently safe by design, fixed guards, or lockout tagout. We can't do the minor surfacing exception. I can't emphasize that enough. If we don't believe we can install and maintain and own these sophisticated circuits. So it's something to keep in mind, particularly the aspects of, you know, the ownership of it. Do we have competent technicians that know how to diagnose, you know, those circuits, be it hydraulic, pneumatic, electronic, the electrical wiring? Is the environment sufficient enough for those things to live in? Is there humidity, temperature, electromagnetic interference and whatnot? Mechanical aspects, shock and vibration and whatnot. Can we put these circuits, you know, is it viable in there? So here's the test. You know, we saw it in the ISO 13849 pass-fail test. So a lot of that is really what goes into the installation of it, and it's not something that should be taken lightly. That any contractor, you know, that installs wiring or pneumatics or whatnot, you really want them to vet them to determine whether or not they're familiar with those standards we mentioned, and whether or not they have some experience with installing safety circuits. Okay, so let's assume we have installed it and we've used a competent, you know, contractor, and we're going to move on now to the next step. Is in there is the validation of it, and this is basically laid out. There's a specific standard, 13849-2, that will lay out the process at which one goes through to validate, you know, these circuits. So again, we are depending on a circuit as our primary means of risk reduction. So what we're going to do in the validation step is we're going to actually try to see if we can get it to fail. So we're going to induce faults in there during normal and abnormal operations. We're going to see, will that circuit fault to a safe state? So we'll mess with the hardware, we'll mess with the software, we'll mess with the wiring of it all, and see if it, in the foreseeable use and misuse of this solution, does it fault to a safe state? And we'll document that as well. The person doing that should be familiar with these as well. There's recommendations that the person who designed the solution and installed the solution should not be the same person who does the testing of it. Sort of like doing proofreading. It's harder to proofread your own stuff than to read somebody else's. What OSHA is going to be concerned about, and what we should be concerned about here, is this concept of control reliability. Really, that's what we're putting to the test here, is in the definitions of control reliability when we're using a circuit like that, is that can the circuit withstand a fault? So we're going to induce these faults. We're going to break wires. We're going to intentionally short circuit things. We're going to disconnect communication cables and see, does the machine stop or get to the safe state? Does it fault, and does it fault to a safe state in every which way we can? So we're going to do all sorts of, abusive stuff to this thing that probably, hopefully, well and beyond what we'll see in its real life, but to see how it will work. So it's during normal and abnormal operations, but we'll look at all of these things. So we'll try to make everything fail in a way and see what happens to it. Further, we'll document all of this stuff, and the person doing the testing, will put their name on it and ensure that, yep, these were tested. This becomes, the part of your archive. I can tell you, there are some companies out there, I'll name Kimberly-Clark as one. If you've ever tried to sell a machine or been involved in anybody from Kimberly-Clark, they won't even consider a machine builder at all if they don't have what's called V&V documentation. That's verification and validation. So that verification we talked about in step 3 when we were designing those safety circuits, we'd use Systema to get a verification report. Did I design this safety circuit to meet the performance level that is reflected in the level of risk in which that is going to mitigate? That's the first one. That's a verification, third-party verification. Now, I'm going to validate this after I install it. Are all my engineering assumptions correct? And did my stop time calculations and whatnot, did all of that stuff do exactly the way it was, supposed to do it? So then I put my name on that. So that becomes part of the archive. So if Kimberly-Clark is buying a machine, they will not buy it until they see the verification, the validation, the V&V documentation. So that's an example of an extremely mature company. You might want to consider that. Test your machine builders. If you're buying machines out there, if you're a machine builder itself, you may consider that as a valuable investment in marketing your machine, that, hey, we're a safe machine builder. So all of that kind of boils back to the first session that we talked about, is the safety maturity level, of the market and the industry or segment customer that you're talking about here. Okay. So we've installed and we have validated, we've documented all of this stuff. So we got a lot of great stuff going. So now what? The contractors leave, everybody's gone, we're running the machine. What happens after that? How do we ensure that these really cool solutions that we're depending on, remember, you're going to have your daughter reach her arm into that machine, and it's only a circuit that's keeping her arm from getting cut off. Think about it that way. Well, how are we going to ensure that that is working throughout the entire mission of the machine? And by the way, the default in the standards anticipate that a machine will last 20 years. So how do we ensure that that circuit will be operating as expected for 20 years? So most companies have some sort of management of change process or procedure in there. The question is, do we have a specifics to these engineered control solutions out there where we are testing those on a periodic basis as well? So again, this should be part of the corporate policies, but the issue comes into when we are talking about, the limits of the machine in particular. How is that machine operating? The temperature, the humidity, all of that stuff. And the recommendations are, if you install a machine in the winter, test it all again in the summer, and vice versa, because the machine will operate, a hot and cold machine will operate differently. So all of those assumptions that we made versus the actual of what we're anticipating, are we seeing that? So we got a choice. We can run this manually, where we have forms and people, doing testing observations or writing stuff down on a periodic basis, or there's the ability to make some of the stuff done in an automated process. So here's some examples of the manual process, but we'll talk about in the next some of the kind of visionary things, and companies are doing this today. How could I automate some of these checks and balances as well? So the question also arises, how often should I be testing these safety circuits out there? And unfortunately, there's not a lot of guidance. In fact, there's almost no guidance whatsoever from the standards. But here's some concepts or ways that we can kind of look at this. The way that I would look at it here is that if I'm using an engineer control as the primary means of risk reduction, I would use that risk assessment to determine, from the start, to what degree am I reducing the risk? So if I'm reducing something from very high to negligible, I should probably test it more often than one that I'm going from maybe a medium to negligible, because you are talking about an investment in time and effort. It probably isn't going to be something that's going to damage a machine or anything, but it will take some investment and some discipline to do this on a periodic basis, and keeping a qualified person to go about doing that as well. So the real issue too is one, the degree in which I'm using this, to how much risk am I reducing it, and then the other part of it is if I'm dependent on these limit values, speed, motion, force, momentum, all of that stuff. If my calculations and my utilization of the engineered solution is deploying or dependent on the consistency of these, I'll say, flexible attributes, we should probably increase the frequency of which those are tested. So take those two kind of considerations, into thoughts, when you are deciding, how often should I test these. Some of the other standards, these involve not just the engineer control solutions out there, but e-stops. If you've got an e-stop testing, that's relatively the same thing. I'm using a circuit, but e-stops, when you test those versus a safety stop, an e-stop isn't something that's typically good for a machine. You want to bring it to a mechanical stop real quickly, kill power to electronic devices. Those things can limit the life. So you don't want to do that too often. But these, if you want to test a safety stop, you can test those as often as you'd like, as long as you don't exceed the number of operations, per year or whatever. But anyway, guidelines at a minimum annually. Lockout tagout, for instance, should be done annually. Testing all of the devices and the process and procedure. As we talked about that briefly in one of the sessions about lockout tagout, having somebody qualified watching another qualified person go through the lockout tagout procedure. So at the same time, you might want to consider testing your e-stops. You might certainly want to test the safety circuits as well to see if they are all operating. So I would say at a minimum annually, but there are companies that do this even as frequently as the beginning of every shift, where they'll test to make sure the circuits are working properly. So it's up to you. What's your acceptable level of risk? All right, so I mentioned earlier, there's a manual way of managing change. There's also the ways to leverage Industry 4.0 or digital transformation, the concept of this fourth generation or fourth revolution out there in industry, and these are the attributes of this. So when we look at the attributes of a digitized manufacturing facility, you'll see those four main components in there, and how they could be used for the safety systems, right in conjunction with they're probably being used, in aspects that affect manufacturing efficiency or OEE. But the safety system can kind of hitch a ride on the Industry 4.0 wagon there as well. So it does require some interconnectivity, some infrastructure. There's information that is embedded in the machine and the machine control systems that can be extracted out. And the whole concept, this kind of gets into a procedural and cultural aspect of it. Do we have the people in place to be able to use that information and interface with the information in order to make some improvements in the manufacturing process as well? So Can the machine itself provide some technical assistance in diagnosing and getting machines back running again? And or can the machine itself make decisions in order to optimize operations? So those are the primary tenets of it. The business outcomes, the benefits of what companies are deriving here, you see listed here below. And those are truly the productivity aspect of a manufacturing facility are really what drive a lot of investments. But as we mentioned before, the chart of a manufacturing facility is to meet production goals at an acceptable level of risk. And certainly risk comes in all sorts of different flavors here: hazards or operational risks, strategic risks, financial risks, all that stuff. But here we have the opportunity to introduce some of the manufacturing safety risks that are involved. So to be transparent with this stuff as well, in the safety in Industry 4.0 does require a couple of attributes for the facility. One is all of that interconnectivity. There needs to be a sort of a control and networking architecture, data capturing historians and whatnot to create data, and then a pipeline and a means to display the pertinent information. So all of this infrastructure needs to be in place. So there's an aspect of integrated manufacturing maturity that needs to be in place, as well as the safety maturity that we were talking about as well. So the culture, the policies and procedures, the technology that's available. But this gets into how sort of the causation aspects, these best-in-class corporations out there, how are they attaining such outstanding productivity numbers and the outstanding safety KPI numbers? So it's this is kind of what we're talking about here, and what we talked about in the past several sessions. This is the causation part of it. How are they attaining that? So the concept of, I'll say, safety in Industry 4.0, and this is, you can put productivity, quality, all of this stuff, and the concept or the flow here is, think of this as, and this is just an example machine. This is a rotary filler made by BevCorp out of Willoughby, Ohio. A machine like this can fill 10 cans of Coca-Cola per second. So 1,200 cans per second come rolling through here. Extremely dangerous machine. This center carousel is whirling very fast, weighs about a ton. So it is got a lot of energy in it. You can see the glass or plexiglass guards that are keeping it. All of those guards are movable because access to that machine is required for cleaning and for adjustments and stuff. So this is a good example of a highly collaborative machine type of scenario. So obviously there's sophisticated controls in there, and inside those sophisticated controls, basically the computer that's running the PLC, that's running the machine, there's data on exactly how that machine is running. And the flow here is to take that data, contextualize it, turn it into information, present it to people or maybe computers that can analyze this and turn it into knowledge. Take some action then and say, let's close the loop on this and make some continuous improvement efforts based on the data and based on the analysis of the information. Let's go take some action. Some examples of the data on our engineering controls that are on this machine are the raw numbers that are going to be housed. They look like this. They're not very helpful in this form, but this is the raw data that would be in a programmable controller data table, looking at the data from the sensors and from the actuators and whatnot. But you'll get raw numbers of these aspects of it. The next step is to then contextualize that, put it in some sort of information process. So a historian or computer algorithms that are going to present it and turn it into information to answer some of these questions like this. How often is that safety system actually being triggered? Why am I down? Why did I stop? Why did I remove power? How often and how long is lockout tagout being performed? So those would be sort of raw information then if I'm reading that information and I can make some interpretations on it, I can start to ask some of these questions and get some answers to it based on real information, not anecdotal stories, not, I'll walk down to the plant. Hopefully one person tells me one thing, another one tells me another, rumors or whatever. But this is, raw actual facts where I can say, are certain individual shifts or areas, better or worse than others? What the when, where, why, how, all of that aspects of it, I can become extremely confident and very certain that I know the truth of knowledge, what's going on out there. And with that, then it provides me with the credibility as an EHS professional or as an operations professional to go and make changes. And I'm not going to run into any resistance out there to say, hey, we ought to do this. Well, why do you say so? Well, I have absolute data to say if we change that, things are going to run better. Okay. So that's the information flow of real-time data to information, knowledge, and taking action. It's credibility and certainty. And then certainly once those changes are made, to monitor those changes again and say, theoretically, this was supposed to improve things, did it, and I'll know for sure. So I'm continually closing the loop. So you'll hear companies hiring data analysts and having software and stuff to deliver this stuff. So let me show you some examples of where this could be utilized. So the ubiquitous emergency stop on every machine. Every machine should have one of these. So what can you get? That's just, I'll say, just one bit in the machine turns on or off. I'm in emergency stop or I'm not. Right? So it's a pretty simple, data acquisition aspect of it. But as we talked earlier about different types of stops on manufacturing machines, the e-stop and the normal stop and the protective stops, or normal stop and cycle stop, right? The same thing. When we're talking about downtime, the implications are significant. You see, just in this example here, if I hit an e-stop, it's going to take me basically 94 seconds to sort of recover from that. And we can know that for sure because there's timers in these PLCs that can count how long are we down, and we can know for sure that a normal stop, a cycle stop, where I'm only down for about 6 seconds. So with that, it's very valuable data that can certainly contribute to OEE. So if I can add some, maybe an operator, if they do hit e-stop, to say, why did you stop? Or if I hit a cycle stop, why did I hit a cycle stop? But I'm probably most interested in those e-stops because that's 94 seconds of production, every time we hit that. And, so I can maybe ask through an HMI, human machine interface device, or even just a set of push buttons and say, I hit e-stop because push the button that says I jammed the machine. Okay. So with that, we can start to, answer, where is that happening? Is it happening for every machine or every production line out there? So now we can start to, find some richer data in here. So I can see, hey, it's just lines 1 and 3, and it's only happening on third shift. So that's pretty good information to go use to say, I might want to show up on third shift, take those 2 production lines and talk to the folks about what's really happening there. Do we have a material problem, a machine adjustment problem, or do we just need to educate somebody on the proper use of the machine? Right. So with that, I can certainly, you can see the productivity on line 2 is probably way higher than these other lines. I can expand that out if I'm looking at multiple plants out there too. Maybe I've deployed these machines or these types of process across plants, and I can sort of share this information with the other plants as well. So when, where, why, how did we stop? Some pretty interesting information just from one single bit that's residing in that PLC. I can find all that stuff out. So we talked about a lot about risk in the first couple of sessions, calculating the probability, severity, the exposure, and the ability to avoid and whatnot. So we did a lot of work and spent a lot of money and time and effort on our risk assessment. There's a lot of rich information on when we did that thorough examination of that machine, how it's operated. The question is, though, what happens to that information once I'm done with the risk assessment? Maybe I've used it to create a functional requirement spec, but a lot of times it's really not used later. So there is some good data that could be used on this machine in how it's operating. For one example here from the risk assessment, we've seen, again, this rotary filler. I've got 10 access points on there. What if I made some assumptions on how that machine is going to be operated by this particular user in here, and I've assumed and I've designed my safety circuits based on this as well. How many times those doors are going to be open? How many times will I trigger that? And every time I trigger that, I'm probably putting the machine into a safe state, which is typically, somehow curtailing productivity. Boy, what if I could track that stuff, and do I really know for sure? So obviously the PLC, every time you open a door, it's going to know, what door is open. It's just an inherent part of the design of the control system. You'll want to tell the operator, hey, door number, whatever that 5, is open. You're not able to start the machine. So it's something that you really should, it's information that's already there. You might as well use it, in a way. So what if we kind of tracked, what was actually happening? Because the PLC knows it. After, you got some runtime in that machine, you put some counters on those doors and put a time frame around it, you can see in a month's time how many what's the actual versus what my assumptions were. So if I put some context around this, now I'm taking that data, I'm going to turn this into some information here. If I say, I kind of want to know, what the percentages of overuse, and from what I anticipated, I would say that, okay, and I'm going to throw some color on it, make it really pop out here, and say, I probably should maybe reconsider, how I design the circuit, or maybe how the machine is designed today. If I'm going to build another machine, maybe, that would be helpful. But these might be our areas here to say, like, they really should be, not opening it that often here, but man, 1,800 times in the past month, that seems pretty excessive. So these are the ones that would jump out right away. Hey, I'm overusing those. But there's one in here that might be one that might be even more interesting here to say, I know access door number 10, there's no way that they can operate that machine without accessing that point at some point during the shift. There's no way. They have to lubricate something or adjust something or whatever. But the PLC doesn't ever see them tripping that safety function. Have they defeated it? Before you'd have to, take a look and see, did they figure out some way of doing that? Well, if I look over the last, again, I'll add some more information, some further contextualization of this. And if this data was available, I could use that. So I could see, over the past 6 months versus this month, how have things changed? Are we running a different product? Did we use a wrong, different raw material, maybe a different can supplier? Maybe something's not working the way it was before. And sometimes that can induce some risk in there as well. Things have changed and the routines are changed, and I've got to go do something different, or maybe I should do something different, with these. So again, it's something where it would be brought to the EHS professional and say, we really ought to take a look at those aspects of it. So you can see how, the risk could be changing, as this machine goes on, and the machine can tell us that. It's pretty cool. Now, reliability. Here's another example why this would be important as well. We all know that these things wear out, and we're depending on these devices and the circuits and stuff to keep my daughter's arm from being removed from her body. I want to know, are these systems still as viable as the day I put them in? So remember our calculation. Based on our risk assessment, we determined that we needed a performance level, a type of circuit, the quality of circuit, and the reliability of a circuit to be at a certain level. So we did these calculations based on that. So if you remember this, this little exercise that was done in an example machine, you'd go through all of these calculations and say, I'm going to use a circuit, and I'm going to trigger that circuit here roughly 70,000 times per year. And when I do the OEE calculations, I determine that the components that I picked out are going to last almost 29 years. Okay. And when I did that too, it then detailed the type of circuit that I'm looking to get, or the performance level which I'm trying to attain. So we know that from the risk assessment. I designed this circuit based on the work that was done. Now our designer said, I'm going to pick out these switches and this controller and these contactors to stop the hazardous motion when I open the sliding door, okay, and expose the operator to the hazard. And I did the first V in my V&V verification, my V&V documentation, the verification aspect of it. I used this third-party software, the verification software, to ensure that I have in fact attained my performance level based on, all of the assumptions about how that machine is going to be used. So here's a field out of the Systema software where you'll actually, calculate the data in here. And we've determined, this circuit, I'm only going to open this door once or twice a shift. So that's really what went into it. Basically, I should only see, less than 2,000, cycles or triggers, per year when I do the calculation based on the information I get from the manufacturers of these devices. This whole safety function, the input, logic, and output, system all together, according to the software and according to the data from the manufacturers, that should last over 2,000 years. So I've got 1,000 times more time, or that I or not 1,000, 100 times more, I guess, cushion, you will, in terms of its longevity than what I anticipated. So all of that was based on this fact. When we asked the operators, how often do you need to get into that machine? They said once or twice a shift. Well, what if the reality was once or twice an hour? My cushion's not only gone, but I'm going to be operating that machine triggering that over 500,000 operations per year, which is not inconceivable, right? So my mission time for this whole safety function cannot even meet the mission of the machine. So I know for sure at some point in the next 7 to 8 years or so, there's a probability that this system could fail to a dangerous state. It could fail to the point where the probability drops in terms of its, or the probability actually increases from 1 in a million to, say, 1 in 10,000 chance that my daughter's arm is going to get her arm cut off, as I reach in there, because and this turns out to be the contactors here will be the weakest link in that whole system. Those things could fail to a dangerous state. The machine may not stop when I slide this door open. And I can calculate all of that stuff based on this software. And I did, and I found out, hey, because the reliability was so low, that my performance level is performance level B. Great news here is that the machine knows this. It knows exactly how that machine is operating. So because we're tracking the use and opening these doors and access functions here, so I can load the criteria for the safety functions in there all the way from the risk assessment, the functional requirements spec, and how I designed it. I said I need these levels of circuits, but the way I'm actually using it, I've got a few areas here that probably should be either reevaluated for a different design or have some preventative maintenance flag put out to say, you know what, I should change those out every 6 to 7 years, right? So that's another example, right? The machine knows how exactly it's being utilized, okay? So we can take advantage of that. The last one's a pretty obvious one. One of the reasons to be connected, to the machine as well, and management of change. When particularly a programmable logic device and the software inside is safety rated solution, once that program is written and it's been validated and tested, it pretty much gets locked down. Right, so it's locked out, and it requires a password to get in there and to make some changes to it. So a lot of times there are issues when somebody goes in and makes some changes but doesn't save it, or doesn't put it in its archive it properly or document it properly. It made some changes. And the machine, maybe it was to address a machine, maybe it was down, maybe we're, hair's on fire, boom, we're trying to fix something like that, and you make some alterations, we fixed it, now it's running. Everybody kind of sigh of relief, but we just let that machine go and run, right? It might be years, but the record of which we had made those changes might get lost. So if the machine sometimes fails and somebody else comes along and reloads the program that they might have had in their archives, they might have reintroduced the problem, that was solved a couple of years ago that wasn't captured. So anyway, we can see all of that stuff, in the PLC. It all knows that stuff, but it has safety implications as well. Maybe some of the changes we made were to improve safety. Maybe the stop time calculation has to be changed a little bit. I've got to bring it down to, or some parameter in a drive that breaks it, brings the thing to a safer stop in a short amount of time. So all of that potentially could be lost, but managing that change and making sure that we capture, the right one can lead into, improvements in safety. So when we look at these concepts, in this concepts of Industry 4.0 or analyzing data, scalable analytics in here too, and we look at sort of the levels of scale of which we implement the utilization of machine data in here, you'll see that from a safety perspective, there's only like the bottom two where I will say it really contributes to safety. The top two, the first two scales in here, and by scaling the system and human, collaboration of it, where we're making decisions and taking action, that data, information, knowledge, action, or decisions, right? The first two in here, when we talk about predictive or diagnostics aspect of it, those can help maybe answer, why did my daughter's arm get cut off in that machine? Doesn't really help the daughter, doesn't really help us in too much of a situation. We really want to get to the level where we are trying to prevent that from happening. Can we predict it and maybe take some action, make some decisions and take some actions? Or if I've got such a system in place where I'm doing some prescriptive analytics, where the machine itself makes a decision or helps the humans support a decision to say, hey, we should make some changes. Maybe I need to change out components, maybe, whatever. I need to change a parameter because maybe I'm looking at, let's talk about stop time calculations. I'm tripping the light curtain, the machine comes to a stop in say 5 seconds. Well, what if over time that stop time calculation, instead of 5 seconds, it starts creeping out to 6 and 7 and 8 seconds when I trip that safety circuit, meaning I'll now have time, and the operator has time to breach the hazard area and reach the hazard itself in that amount of time, where before, when it was 5 seconds, they couldn't possibly get to it. Now it's 8 seconds, they can get to it, and years have gone by. So what should I do in this case? If I'm the support decision, the prescriptive part of it would maybe send a flag to maintenance and say, hey, the brakes have worn out on this thing. We should probably readdress this, have some sort of flags, some information delivered to the pertinent people. In a case where the machine itself would make a decision, the machine may slow itself down, it may not allow you to hit maximum speed. It begins creeping back. So my momentum is not so much, and my stop time calculation stays at 5 seconds. And maybe it curtails productivity a little bit, but I'm still not going to get an incident out of that. So that's just some examples of the scalable aspects of it. Some of the, so this leads us to, what if all this sounds really great, why aren't we, why isn't everybody doing this? And I mentioned, the two elements of maturity, the infrastructural digitization maturity, as well as safety maturity, both have to be in place. And you can see as an example of a study that was done to say, why don't we do stuff like this in here? And you can see the top two that do make sense, and they're somewhat interrelated here. Is that one, the systems that are in place, or maybe they're old, maybe they didn't have the capability and sophistication to pull all this stuff off like before, or like the current stuff does today. Maybe they put it different eras, or maybe you have a whole new machine, but not everybody was participating in their ideas of how that gets into the cross department collaboration. So if we have let's say, some political divides between the different elements of the company and different charters, operations, EHS, engineering, executives, maybe all of that, is not collaborating to the degree in which it could. You could end up with disparate systems, as well, that don't contribute in a cohesive way to all of these concepts of what I'm talking about. So the Industry 4.0 is probably the hottest topic in the automation world right now. So it's a pretty good chance that those conversations are going on today at your enterprise or at companies around the area, because boy, the fiscal benefits of digitizing and using information to manage a facility is without question. So the popularity of it's great. So these are typically the folks and the roles that are involved in, I'll say, the journey of digital transformation. And there's one missing in here that typically is not participating, but probably should be in order to begin to infuse this. So go back to one of the original designs or aspects of risk reduction: inherently safe by design. Is EHS, does the safety department have a say? Do they have the credibility? Are they recognized as a viable contributor, to these journeys and the manufacturing facilities? Because here's what's being discussed in those. The whole plan and the infrastructure that's going to be put in there, and then the list of information, the types of information that should be delivered to the pertinent people to be turned into knowledge, that are extracted from the machines. And then, how well is everybody collaborating and cooperating, amongst the entire enterprise? So these four elements are the sort of the four main tenets of Industry 4.0. Again, this is, really coming down to those two attributes of maturity. Is that infrastructure being put in place, and is safety, considered in those conversations? Is safety a good fit into the business strategies of the organization as well? If it is, and maybe we're at a point where we're just thinking about these kind of infrastructures, these improvements, could safety even be the impetus to do this? I could tell you, a number of companies that have used safety as the main reason why they went through a major transformation. I mentioned Paul O'Neill and Alcoa as some very early examples of that, but there's examples I could share with you about the Dana Corporation or Goodyear, a number of other companies, that have used Procter & Gamble, Mondelez, General Motors. They use safety as a reason to put this infrastructure in place, because the safety maturity is so strong, it begins to then dictate some of the manufacturing strategies as well. So here's the idea, for safety professionals to get involved in those conversations as well. If you have put these systems in place, automated safety solutions, these engineer controls in place, then there is a reason for you to be involved in those conversations here too. So look at these items, come with an understanding of what kind of information do you want to access from these machines, and where do you want it delivered? How do you want it delivered? What knowledge do you need in order to improve the safe manufacturing performance of these machines? So that's it. That's the machine safety life cycle. That's it. That pretty much wraps up the conversation about this. And I'm hoping that, we've got some ideas. This is the ubiquitous flow. Every machine safety standard out here will take us around and around this. And you can see this connecting arrow, the continuation of this. This is a cyclical aspect of it here too. It's meant to be done over and over again on a continuous basis, much like, any aspect of continuous improvement. So as we saw, just a kind of a quick recap of these 5 sessions in here: the societal demands, the aspect of the safest companies in the world are the most productive. And that secret is getting out, and more companies want it. They're utilizing new techniques and technology and concepts, manufacturing techniques, and that has driven a demand for recognition of some of the existing laws that are out there, but revisions of the standards to, take advantage of that. Every day there's some new technology that's out there that challenges the status quo, that is being driven by these demands and these standards and the laws, and is sort of the law of a capitalistic society to continually improve. So that's kind of the recap of how companies attain this. The safest companies in the world are the most productive. The data is very clear on that. So anybody still with the perception that the only way to be safer is to sacrifice productivity should really reconsider that conversation and or that thought, and realize the safest companies in the world are the most productive. And it can lead to some tremendous improvement. If you've ever read the book Good to Great, for instance, how do these companies become good place, great places? A lot of it depends on people and the type of people that you have, the quality of people you have in place. So the ability to manufacture in a safe, responsible way can lead to a company's greatness and the people beyond it. So, and then ultimately as a corporate citizen in our society, it's simply the right thing to do. This concept of corporate social responsibility should be rich environment for us to generate some justification, to at least have the conversation and be involved in it, as well. So if there's any way that I can help you, with those conversations, be it internal, external, if you just want some ideas, feel free to reach out to me via phone, via email. My contact information here too. I'd love to talk to you about and provide some guidance. I spent now almost 40 years in the automation industry, so I've seen a lot of it, and a lot of it has been involved in the machine safety aspect of it. One parting, just because we have just a minute here, I just want to take a minute to point out my favorite TED Talk. One of my favorites because it's only 3 minutes long, but it's a fascinating and very pertinent to what we're talking about here. If you are inspired by these 5 sessions here too, you need to become that inspirational entity within your enterprise and to get the ball rolling, start a movement in here. And that's really what this is about. It's a quick social study, science, a social study that shows how does a movement get started in here too. And it's a fun one too. The presenter is great, but it starts in a lawn, the lawn seats at a concert, and you see this one crazy. Everybody's just sitting there listening to the music. One guy gets up, starts to dance, and then he goes through how the mob scene changes from his first followers and a little group, and how he celebrates those followers. And before you know it, you see in 3 minutes, this one crazy shirtless dancing guy gets the entire lawn dancing, but he relates it to kind of human behavior aspect. So it's 3 minutes. So as you're trying to, start a movement, with your multiple entities of your enterprise, operations, EHS, engineering, how do you align all of those in there, the leadership within that? How do you take that to the executive level in a unified perspective of operations, engineering, and EHS, all wanting the exact same thing? So when we talk about this change equation that's up here, think about not just the dissatisfaction, vision, steps, and resistance to change that you've got as a safety professional, but think about operations and engineering as well. Collect all of those and get agreement amongst those, so that these columns, of what do we want to go do and change, are aligned, throughout the entire enterprise. So take a look. You can just search on this guy. I can't remember his name. Derek Sievers, I think is the name. But just how to start a movement, Derek. I think you'll get it on TED Talk, and it's an entertaining, worthwhile 3 minutes. Take a look at that. So with that, that's a wrap, and hopefully maybe we got some questions or comments or bullshit flags or whatever you want to throw here. We're open to discussion here, Mike and Nick.
Hey, that video is great, Mark. I've saw it years ago and I watch it time again. It's definitely entertaining, and you never hear anyone talk about leadership in regards to the first follower. So there's definitely some insight in there of how to get things going and focus on that. It's kind of like a creative way to talk about the 80-20 principle, where you got 20% that do 80% of the work. So you focus on the 20% and you'll get more productivity. So it's kind of cool. Nick, is there any questions out there?
I didn't see any questions pop up in the chat today, but they do have your contact information. It's on the screen here. Mark, I just want to say thank you again. This has been really insightful for me, and I'm sure it has been for our members too. Just lots of good information, and it just helps us start to think about how we can make our machine safer, but also how do we change culture? Because there was a lot of culture nuggets throughout this presentation. And that's a big part for me as a safety consultant. When I walk into a company is what the culture is. The culture will define how their safety success will be in the future. If you have the right culture, they buy into machine safety, right? If they have the wrong culture, they're not going to buy into those pieces. So once again, thank you so much for this information. Great stuff. We have stuff coming in from people right now that says, thank you for the great information. I think it was very valuable for all of our members, and we appreciate you taking time out of your busy week for the past 5 weeks to do this presentation for us.
Yeah, absolutely. And again, if somebody wants to share this story, we can parse this up if you want to do a full day, on this with multiple entities from your enterprise, executives, HR, legal, all in the same room. You can have some great conversations. If you have a safety council and you want to, do this for the entire safety council, we can parse this up. I'm dealing with one right now. Useful that I have, this online version of it. We're going to do very similar to what we just did here too. We're going to do 5 lunch and learns. It's 60 to 90-minute presentation, and then the safety council meeting. Afterwards, they'll talk about that as a council and see, do we want to take any action as an enterprise, as the safety council, giving them, all sorts of great ideas of what they can do moving forward. So happy to participate in any and all of that, however I can help.
Yeah, Mark, we're going to email all the video links out to everyone on our email list with your PowerPoint slides and all that stuff. So we'll get the information out there as well and help push it out a little bit more. So we definitely thank you. There's so much your information is so rich. I think people could watch this 3 or 4 or 5 times and still get new things out of it.
It is deep and broad topic.
That is one thing that I was thinking about. I mean, I'd love to sit through a whole day workshop with you on this, but I also feel like at the end of it, my brain would be a little exhausted and I'd have to dissect that for a while and probably come back with lots of comments.
Yeah, for sure. It's exhausting for sure. But hey, today it's unavoidable. So
yeah, no, it's important stuff. And I just hope that we can get more CEOs, senior executive, the C-suite staff to start paying attention to pieces like this and understand that while it's hard to put a direct dollar amount on safety and what it's saving you, it does make your company better and it's going to help you lead change. And in today's environment, it is so important. The market is changing so fast. COVID has forever changed how business is going to operate. We were just talking about that this morning. Staffing levels are different. Supply chains are different. Manufacturing processes are changing. So this is of the utmost importance, I think, for our C-suite staff to start thinking about this and how you're going to succeed and really lead your industry moving forward.
Yeah.